Hello and welcome to Angles and NASA, where we learn things maths and science. In today's video, we're going to do forces. Finally, a science topic for once. I know it's been a while. I've been doing a lot of maths videos. We've been studying biology a lot, and it's not my forte, but physics and chemistry definitely are. So let's get into that. Forces. What is a force? A force is basically a push, a pull, a twist, and if you've got a combination, you've got two opposing pushing forces, you'll get something we call shear force. And these are contact forces. So what happens when you do these actions? So if you push something, if you push an object, like a cat pushing things off the table, obviously that object is going to move off the table. If you really want to get technical, and this is stuff that we would talk to, in grade or high school, when we say that a force moves objects, basically the technical definition is that it causes the object to accelerate. So as you have like let's say the ball is coming towards you and you hit it with the bat, for that moment of impact, when you push the ball with the bat, you are basically changing its direction and applying so much force that you're accelerating it. So it goes from high speed to no speed, and then you push it back up to speed again. So when you increase the speed of an object, you are basically accelerating it. The longer it stays in contact with the ball, greater the stroke of the bat or the golf ball, or a golf club and stuff like that, basically the more time you have to increase its speed. Once the object leaves your bat, however, you're no longer pushing it. So what happens then is it's basically traveling by its own momentum, its own inertia. So it just stays at a constant pace until eventually it's slowed down by air and things like that. So forces technically cause things to accelerate, but simple terms, let's just think about it moving things. So if I push the object, it's going to move off the desk. If I pull an object, it's going to come towards me. If I twist something, I can basically do things like this. So twisting, obviously opening up a jar. I got my wife to loosen this one early for me because I'm not as strong as her. You got your push and you got your twist. You've got your pulling force. Oh, that actually worked that time. Shear force, however, is when you've got two opposing forces. So you've got one force coming in this way and one force coming this way. If they're close by at a particular junction, they're acting like this. The space in the middle is basically going to be like, if I have a bolt, for example, so this happens to bridges. The bridge is bolted to the pillars, all right? All the way down the bridge or highway or overpass, whatever it is. So the deck bolted, to the ground through the pillar. These bolts are metal, so if there's an earthquake, the beam, the top of the bridge, the deck, is moving with the earthquake, and that can move in such a way that it's moving basically off the pillars, and so you basically have that bolt being subjected to shear forces. And if you haven't designed your bridge very well, then the shear force might be so strong that it actually snaps right off or shears right off and your bridge falls over or falls apart. So that's a consideration when people make bridge designs, particularly in earthquake zones. So, all right, so these are known as contact forces. Let me just tie off shear forces. Basically, everyday objects is scissors, all right? So I don't know if this is focusing. My monitor above me is not working. But basically, the scissors do the exact same thing, okay? So instead of an earthquake, let's turn it earthquake scale. So I have one blade moving in this direction, the other blade's moving the other direction as I close the scissors. That means that at the point of contact, right in the middle, I'm taking a very small portion of material and subjecting it to two opposing forces. And that basically is so strong, that pressure at that point, that I can basically cut things apart, okay? These are contact forces: push, pull, twist, and if you've got combination, shear force. What about non-contact forces? Because there are other things that act upon us even though they're not touching us. So the main one that we experience every single day at every single moment, even before you were born, well, maybe not before you were born, is gravity. So you feel the force of gravity every day. So what is gravity? Well, it turns out because our planet is so large, in fact, Isaac Newton sort of discovered this sort of principle, is that the larger the object, the greater the pull it has on other nearby objects. It can draw them to itself. Now, so that means that I have gravity and so do you. But the reason why things don't go flying and sticking to you very much the same way that you jump off a building, you fall back down to the planet. The reason why that doesn't happen to us at our scale, on a human scale, is because obviously we don't have as much mass. So we don't have as many atoms and molecules and things like that that we're made of. There's just not enough of them to really have a significant amount of gravity to see things stick to us. But the Earth is so much larger, it's on a scale that it's so much gravitational force that it actually pulls every object, trees, buildings, tennis ball, satellites, the moon, and it can even draw to itself other planets. So no matter how far away they are, they still feel drawn towards the Earth. It's just weaker and weaker and weaker as you get further and further away from the Earth. It doesn't mean it's not happening. It's just further away, therefore weaker. So gravity, it pulls us to the ground. It's not touching us. So if I jump in the air, I'm not touching the planet, but I'm definitely pulled, accelerated to the planet, which is the reason why when you fall, you start getting faster and faster and faster and faster to the ground. So that's the whole force causing things to accelerate. Other forces, we've got magnetic force. So if I've got a magnet, I can make iron and other things feel drawn to it. In fact, with magnetic force, I've got a little compass here on my table. So basically, the Earth itself is magnetic. Okay, we think that the center of our planet must be made out of the very few metals on the planet, very few metals in existence that actually is magnetic. So we think that it's probably made of iron. And that iron being very hot, and I think it's moving, I think that's part of the reason why we have a magnetic field around the entire planet. So we actually have a north and a south pole, and that's what these compasses respond to. They actually adjust the needle because it's floating and it's not subjected to wind. Okay, since it's covered, it's in its own container. It's not subjected to wind or anything like that. It's designed to be floating as much as possible, isolated, such that it can freely spin and align itself to the Earth's north and south pole. That's how we find north and south. So we got magnetic force. We've also got electrostatic force. Now, I don't have any equipment or things with me right now to create an electrostatic force, but basically if you have access to a rubber balloon, you can basically rub it against your hair. And by having two different materials, like your hair and the balloon, if you rub them against each other, you'll create a separation of charge, and things will feel drawn to it. So your balloon will stick to your head, or you can get other bits of light, bits of dust or paper bits will actually stick to the balloon. So you can do all kinds of cool things. Electrostatic force, it draws things to itself at a distance. Okay, let's move on to other things about forces. It turns out that at any point in time, it's very rare for only one force to be acting on an object. Most of the time, it's going to be multiple forces. So the fact that I'm sitting in a chair right now, I am being subjected to multiple forces, okay? So obviously we talked about gravity. So that's happening right now. It's keeping me on the planet. If gravity force stopped working right now, I would fly away from the planet. I'd probably fall, let's see, depending which way the Earth rotates, I probably wouldn't fly this way. I'd probably fly that way or that way. When gravity turns off, but I'm sitting in the chair. My mass is being pulled to the Earth, so it keeps me firmly seated in my chair. However, why don't I continuously fall through the planet? Well, obviously I'm being supported by the chair. So the chair is giving me an opposing force. Now, if you think about if I'm pushing against you and you push against me, if we push against each other with the same strength, then we cancel out. I think you can agree with that. So if I'm pressing into this chair, and I'm not winning, okay, so I'm not sinking, that means the chair must be opposing me with equal strength of force. So we call this, technically, it's called a normal force. Normal, which comes to, related to right angles, okay, I think it's a Roman or Latin word, normalis, which means orthogonal to, or 90 degrees to. So if I press against the surface, basically I'm being resisted by an opposing force from the opposite direction. So that's two forces acting on me right now. So if I sit in this chair and supported by a chair and I spin, obviously there's multiple forces going on at the same time. Obviously you got that motion, the twist motion, as well as the gravity force and the normal force supporting me in my chair. Let's look at another example. So what's this over here on my table? Oh, I made little parachutes. So I don't have a little G.I. Joe. I don't have anything cool. I know these are very rare nowadays with the lack of plastic bags. But basically a parachute. So if I lift it in the air and drop it, it's being opposed by different forces. So obviously the parachute is being drawn to the earth by gravity. So it's being pulled by gravity. That's one force. When I'm holding it, so I'm holding it in my hand right now, I'm actually opposing it. I'm opposing gravity by applying a little bit of strength in the upward direction to keep it here at the same position, to cancel out the effect of gravity. But if I let go, which I'm not going to do right now, but if I let go, then basically gravity takes over. Once gravity takes over and it starts accelerating down to the planet, it's going to encounter a lot of air. Okay, so air is going to come in beneath the bag and inflate the bag, and it's going to basically catch a bit of wind and slow it down. So it's going to oppose the direction of motion. So we call it moving in this, opposing it in that direction. But also the fact that this thing has quite a bit of shape. So it's got a bit of volume, right? That means that as it tries to flow through the air, air has to either get inside or has to go around the object. When air has to force to go around the object, it's actually rather difficult, okay? So it's going to encounter quite a bit of wind resistance to try and move around the object, and even more so, particularly behind the object. You can imagine there will be a lot of air rushing around the sides as it falls through the air, but very little air right behind the object, okay? So in fact, there'll be less air molecules in this region right in the center of the bag at the back than there would be a lot of air particles around here. So what happens here is we basically have a suction. It's a vacuum, a slight vacuum, not a perfect vacuum, just a little bit of a vacuum. So it's actually trying to suck the bag upwards, just a little bit. Obviously, gravity is stronger than all of them combined, so gravity wins and it continues to fall to the ground. So multiple forces. So obviously you've got gravity pulling it this way. You've got wind resistance, which tries to oppose the direction of gravity, oppose the direction of motion. You've also got a drag, which is that sort of vacuum that's of space behind the object when it's moving through the air. You get a bit of drag with cars, a ball flowing through the air. Basically, it's that spot behind it. So multiple forces at any time. I know this is taking a bit long, but I get really excited about science. All right, last one is that we have force arrows. So how do you show what forces are acting on an object at any time? Well, we basically draw arrows on the object. Okay, so let's say I've got this guy in a parachute. We basically show the forces by using arrows. We call them force arrows. The longer the arrow, we would signify that means it's a stronger force. If it's a shorter arrow, it's a weaker force, okay? So for this guy who's in the parachute, by convention, we draw force arrows out of the center of mass, the center of gravity. So for a person, that's usually around their belly button, the center of mass. So we would draw the force arrow coming from their belly button and outwards. The longer the arrow, the stronger it is. So not only is he being pulled down by gravity, so force, and you can put a little g here for gravity, you're also going to get opposing forces. So we're going to get a little arrow moving in the opposite direction, just smaller. And this will be a force of, resistance, drag, and all those other ones combined. Obviously, I'm drawing this one in a smaller arrow because gravity is obviously winning the day. Until this object goes so far, I'll actually go about this in a different video, but you do get to a point where the object goes faster and faster and faster, which means that you get more and more wind filling in that parachute, and then eventually the resistance, the drag gets so significant that the force of gravity and the force of resistance and all those things combined are equal. So what happens when forces are equal? Well, they cancel out. When forces cancel out, doesn't mean nothing happens. Obviously, the person still comes down from the sky. But what happens is that acceleration stops, okay? So yes, if I press into, another person and they push back just as hard as I do, we don't appear to be moving. However, that's not the only case. If we were both on rollerblades and we're gliding this way, and we're pushing against each other this way, maybe that's not the best example. But basically, you're either going to have no motion or you're going to have constant motion, meaning you're just going to coast. Okay, you're going to have a consistent speed. I think I've elaborated this one far too long in this video. I will wrap it up for now. I hope you enjoyed the video about forces, and I will catch you in the next video. Thanks, guys. Bye.